live watching now. Qua ci sono?
Sì.
Shall we start?
Stai un po' più vicino?
Forse è meglio se proprio luce accende se non si vede. Forse ci passa un estremo. Facciamo in vista centrale c'è la luce lì.
Una linea metà.
No, così è diviso 1, 2 e questa è la sì. Un attimo slide.
No, ma anche con la luce va bene. Si vede un pochino di chiaro lì.
Se non puoi dare una.
Ma non è un... cioè si vede abbastanza bene comunque.
Poi accendi vista e allora fa grigio.
Ma sai che forse con la luce è peggio, molto peggio.
Quell'altra?
Non sbaglio prima. Così va bene secondo me, se si vedono così è meglio.
No, sempre no.
Sì.
Così forse è meglio questa.
Così va bene secondo me. È un pochino in ritardo così.
Dopo la sì, c'è 15 secondi di delay.
No, questa, non questa, è meglio quella in parte, altrimenti così è.
Quella in parte...
Come prima, no?
Quella in parte o
Sincronizzate diciamo questa.
Spero. Così forse è meglio questa.
Okay. Shall we start? Are we live now?
L'audio c'è? Sì.
Okay, good morning everybody, people here in the room and people listening to us and watching us on YouTube. By the way, you can also comment online and you can read your comments. So welcome to the 2016 workshop on future systems, security and privacy. This is a workshop organized by the Spritz Security and Privacy Research Group here at the University of Padua in collaboration with Lucid, which is the Italian Association for Computer Security. This is an event organized for the European Cybersecurity Month in 2016. Let me just thank the organization that helped organizing this workshop, like our Department of Mathematics, the HIT Human Inspired Technology Research Center, and the Packet Smart EU project that will be also introduced in this workshop. Just a quick overview of the speakers. We will have 6 talks on cutting-edge, published and even unpublished research. The first one will be Riccardo Lazzaretti, which is a postdoc at the University of Padua. His talk title is Odin, Obfuscated-Based Privacy-Specific Consensus Algorithm for Decentralized Information Fusion in Smart Device Networks. Second talk will be by Riccardo Spolaor on an interesting talk about profiling application to smartphone application to encrypted traffic. The third talk will be by Daniele Lain, which is a talk about a very interesting attack, a novel attack on Skype, or in general voice over IP technology on acoustic eavesdropping on voice over IP. The fourth talk will be by Morena Ambrosil, will be a novel protocol to update billions of devices in the IoT framework, leveraging cache-enabled networks. Then we will have a presentation about our Target Smart project the Spritz group is involved in. And finally, Alberto Geretta, with a nice privacy-preserving picture, will discuss about BioNanoThings, which is a novel proposed technology, and we will take a look at security issues in these novel networking technologies. So thank you for being here, for watching us streaming on YouTube. So I think we can start with the first talk by Riccardo. Thanks.
Good morning, I'm Riccardo Lazzaretti. I'm going to present ODIN, an obfuscation-based privacy-preserving consensus algorithm for decentralized information fusion in smart device network. This is a joint work of me, Morena Ambrosil, and Professor Conti from the University of Padua, and Paolo Braca from the Center for Maritime Research of NATO in La Spezia. This work is submitted, is under review, so it is not possible yet to find it on Scholar or something else, but it will be uploaded on archive soon. Okay, during the presentation, I present the motivation and the goals of our work. Then I'll describe the consensus protocol, and I show the state of the art in privacy-preserving consensus protocol. I'll introduce the cryptographic tools quickly before to provide the implementation. At this point, we analyze the protocol and we provide some conclusions. Information fusion is the keystone of many systems in the Internet of Things, where we have a decentralized environment and we have to take decisions on some consensus. The consensus is simply the mean of the observation provided by Internet of Things devices. Information security is a crucial aspect that is already addressed in several works, where we are going to protect the systems against outside attacks that inject false data or among other attacks. But information privacy is often neglected. What does it mean? I mean that there is no protection between the privacy of the data involved. Each people, each node involved in the computation can be interested to protect the data that other nodes observe his data. For this reason, we need privacy-preserving solutions that allow secure cooperation among non-trusted nodes. In such a way, each node is able to observe only his observation and the final decision of the network. As I said, the goals of this topic from the agent is interested to take a binary decision on the consensus of the network. This consensus is the mean computed among all the observation, and the observation of the final decision has to be kept private, means the semi-honest. Intermediate values involved in the computation cannot be observed at any node. From not a security point of view, we need that we have not a central unit that is performing all the computation. We can consider that the network is not fully connected, and we also are interested that the solution can work on dynamic networks, where nodes can change their position or can be disconnected for some interval of time. Now I describe the consensus networks. At the beginning, each node has an observation of an event, that is y0. They perform several update steps, and in each update steps, two agents, two nodes are cooperating, and both of them are updating their observation with the mean of their observation. At this point, by performing this operation, the observation of all the nodes converge to the mean. After a while, given interval that we can, it can depend on different strategies, a decision is taken on the observation of each node. That is, they simply compare the consensus with a threshold. In practice, we can consider that, for example, the first step, node 6 and 7 are updating the step, 5 and 2 in the second step, 7, 9 in the third step, and so on. From the point of view of a single node, obtaining the input measure, it waits for a while, take a pause, then it chooses an adjacent node, perform the update, and then decide if you want to take the final decision or continue. If it is you want to continue, it wait for an interval, update again, and so on until at the end they decide to evaluate the final decision together with an adjacent node. We already have a solution presented on iCasp by me, Paolo Braca, and Horn from and Will. This solution is based on homomorphic encryption for the update step and garbage secrets. It has some problems. First of all, it can be applicable only to static networks, and moreover, it has a high communication complexity because at the end of each step, each agent, each node needs to perform some computation to let the other node able to interact in the following node with any of his agents. For this reason, the complexity depends on the number of neighbors each node has. In this implementation, we are using additive blinding that has a really high efficiency and proxy encryption to perform the update step, it again for the final step. This is important because by using proxy encryption, we have not a complexity that does not depend anymore on the number of neighbors. Additive obfuscation, what is this? Simply, if Alice have a value x, it can choose two numbers, a and b, randomly, and compute a times x plus b to blind this value. Y is transmitted to Bob, then evaluates a function g on y and sends the results back to Alice. At this point, Alice can obtain f of x from g of y. There is a linear function that depends on g, something computed on a and b, s, and the other function again computed on a and b. It is impossible or really difficult to recover x from y, and but here see, we are using only additive blinding, that is to x we add only b or x, and we are considering the operation in modulus m. Proxy encryption. Proxy encryption is a really interesting tool, really useful in our applications. Let's suppose that Alice has the encryption of a message with his public shared to Bob, and Bob is able to perform a proxy encryption by using an encryption key between Alice and Charlie. In such a way, he can obtain an encryption, the public key of Charlie, of the message. This message is sent to Charlie that is at this point able to decrypt. By using proxy encryption, doesn't know who will be Charlie. But Bob can decide who will perform the decryption, who will be the final destination of the message. It is only important that, of course, Bob is not able to re-encrypt the message in his private key. Double secret is an interesting, a really powerful multi-party computation tool that allows the secure evaluation of any Boolean secret on private input, where one party, here I don't go into details, but one party encrypts the Boolean secret, the other party decrypts the Boolean secret, and by using oblivious transfer, we guarantees that a party is not able to see the inputs of the other party. It is really powerful because with it we can, in theory, evaluate any function. The problem is that it has high complexity, but for the final decision step, we'll see that it has an efficient implementation. Before to start the protocol, we need to configure the network. Each agent I shares its public key through the networks, receives the public keys of all the other nodes, and generates an encryption keys between his public key and the other public key. At this point, he shares the encryption key to any other node. When sharing the encryption key to J, of course, he shares all the public key except the encryption key between I and J. Of course, this can be done, can be optimized by sharing only the encryption key with the adjacent nodes, and we can easily adapt this optimization to also only with dynamic nodes. We have some details in the paper about this. To work with obfuscation, blinding, double secret, we need to represent each value with integer number. A first idea could be to simply amplify the measure with an amplification factor, Q, and round to the closest integer number. The problem is that during the computation, the bit length of the values increase after each step. For this reason, we are going to represent each value as the ratio between a numerator and a denominator. And in the first step, we consider that the numerator is equal to the observation, if it is an integer number. Here, I consider only integer numbers for simplicity, but of course, we can adapt with the correct number. And the denominator, this is the same of the archive period. At this point, we need to evaluate the steps. The input of the agent I and the network J to each of these steps, agent I owns the numerator branded with an obfuscation value that is generated by another node K, with whom I performed the previous. Similarly, J owns the numerator branded with another value chosen by another node L. In the first time that they participate to the consensus, of course, they input their measure. The denominator of I and J are considered public. I will discuss later about this. At the end of each step, the agent I will obtain the new numerator branded with a random value chosen by the node J, while agent J will obtain the numerator branded with a random value chosen by the node I. Here, I think that it is impossible to see it on the streaming, but the idea is that agent I, I'm going to observe only agent I. J is performing the same operation. Agent I choose two random values, R and S. It has the numerator blinded with the branded value with chosen by K, a random number. Then encrypts the blinding value with the encryption key of J and sets numerator blinded the encryption of the random values and the denominator to J, and receive the other similar information from J. At this point, I decrypt the obfuscation provided by J, remove that obfuscation, obtaining a numerator blinded with only a value provided by J. Compute the new denominator, simply by the least common multiplier, and at this point, computes the new numerator by a simply linear product. We see that this, we can see easily that this numerator, the new numerator, is blinded by an obfuscation that can be computed by J, because this obfuscation depends on values that J knows. And then I finally add another obfuscation. This value, this numerator, is at this point transmitted to J, that is able to remove the obfuscation, and finally obtaining the new numerator blinded with a value known by I. This point, as I said, can the denominator be public? Yes, because it doesn't carry information about the original value. It depends only on the step that performed. So if the denominator is 8, it means that we had a sequence of updates of 3 updates maximum. Moreover, it is important to note that the denominator can be used when performing the final step, because if the denominator is really high, it means that many of these states have been performed, and okay, maybe when we have an high denominator, okay, this is the moment to perform the final update step. The final update step is performed by using the secret. After having performed the update together with the agent J, I can ask to J, okay, please help me to take my decision. It inputs the numerator blinded with the blinding value provided by J. It inputs the threshold, his threshold, by the denominator. Agent J input to the circuit the blinding value. At this point, the circuit simply remove the blinding and compare with the threshold. At this point, the decision is provided to I and J, if we decide that also J obtains that. We can also modify the circuit so that also agent J input is a threshold. They can have a different threshold. Okay, here I consider to perform the modular operation, but we can also modify the update step to avoid the modular operation, because it is a bit expensive by using update circuit. Now I'm going to analyze the bit length of the values. We consider that the starting input is represented with L bits. We can simply see that after k steps, we have the bit size of the numerator that is lower than L plus k. We can see that the bit length of the input is not going fast. But however, if we are going to exceed the modulus n, we can perform a modified update step that reduces the bit size, simply dividing both numerator and denominator for the same factor. We have, I'm not describing it in the detail. Here this complex slide is talking about the convergence. Simply the convergence of the network depends on the structure of the networks. But it is easy to demonstrate that usually it converges. Talking about complexity, this protocol, we can see here that as a number of fixed number of modular exponentiation, exactly 6 modular exponentiation computed for any of these steps. and they are performed in values quite small because n is not a huge number. While in previous work we had a number of modular exponentiation that depends on the number of neighbors of I and neighbors of j plus 8, and we have to underline that these exponentiation are performed on really big numbers that are around more than 2,000 bits. Moreover, we have 4 modular products and 2 bilinear maps for the proxy re-encryption. You can see that also the communication is limited. We are going to transmit less than 22 small numbers, while here while in the previous implementation we are transmitting huge numbers, huge ciphertext, and the number depends on the number of neighbors. The final step is really similar, it's quite similar, but also in that the complexity has been decreased, principally because we have no more the conversion between IA homomorphic encryption and the double secret that needs 2n exponentiations. One of the main issues raised during ICASP presentation was, okay, but can it really work on low-power devices? Test. But we tested this implementation on Raspberry Pi 1 and Raspberry Pi 3. We can see that the runtime of an update step is around 100 milliseconds on Raspberry Pi 1 and 40 milliseconds on Raspberry Pi 3. The energy consumption is 240 millijoule on Raspberry Pi 1 and 88 millijoule on Raspberry Pi 3. The final step has required less time, 25 milliseconds, and 55 millijoule for Raspberry Pi 1, and 19 milliseconds and 40 millijoule are the complexity on Raspberry Pi 3. About the security, we can see easily that the security is guaranteed in the semi-honest model. Additive binding always guarantees that no node is able to obtain the numerator, because every time it has a numerator, there is also it is obfuscated with a random value chosen by another one. Any operation performed, add a noise or remove a noise, there is also each time another value obfuscating it. Proxy encryption allows to share some obfuscation between nodes, but if the setting is performed correctly, no nodes will be able to defeat an obfuscation affecting his numerator. To conclude, I presented Polin, that is a more efficient privacy-preserving implementation of the consensus proxy algorithm. As desired, it was without a central unit, and it can be also applicable to dynamic networks. The security is guaranteed in the semi-honest model, and its implementation is based on additive obfuscation, proxy encryption, and double secret. Now we are interested to develop, to propose a new algorithm that can be also secured in malicious settings, where nodes are not only interested to observe the values of other nodes, but also to modify the consensus. For example, injecting false node, continue to use the same input value, in such a way that the final consensus is modified. And we are also thinking to possible applications on Internet of Things, on drones, and something else, where we can use OVI. for anyone that can be interested in the topic. We are happy to collaborate, to hear new ideas, etc. So, okay, that's all. If you have any question, I forgot the question slide. Sorry. Any question?
Yeah, one question is whether you can detail a bit more possible applications, like in the military environment.
Okay. Our first idea is to use drones, for example, to use these to allow the cooperation among nodes. Let's imagine that a swarm of drones needs to explore an area. In this area, they don't know what they are going to see. They only know that they need to fly from a position to another one, possibly not linearly, but spreading in the area, and arrive to the destination. During the destination, they have not a central unit they can communicate with to, okay, now where I have to go, I don't know. They have to take decision autonomously. And they can only interact with closest drones because they have limited communication range, because they don't want that possible attackers, physical attackers, far from them is able to observe. And they can use Odin so that, okay, they can compute the density of drones in each section, in each portion of the area. So that, okay, if in this area here, there are already 5 drones, a drone here can decide to go here. Such a way they can distribute among the area. And moreover, they can also, a drone that, okay, it is in a section and maybe it's observing that there is some danger close to him, it can highlight to the other drones that, okay, this is a dangerous area, avoid to go here because there are missiles, there are enemies that can capture you or something else. Or differently, if there is something of interest in a position, drones can use Odin to increase the interest of this area so that more drones are going there and observe what and take measures to have more accurate measures about the event that can be, I don't know, a missile station not used in that moment or something like that.
Okay, other questions?
Online questions?
No.
Okay.
Okay, there are also no questions from online.
Okay.
So
Let's consider for people attending the event on YouTube, there is a chat on the right of the screen where you can write questions for people presenting. Okay.
Thank you.
Next presentation is Moreno.
You might quickly introduce yourself. This is good for
No,
your
this is
presentation.
my presentation.
Sorry?
So good morning, everybody. My name is Moreno. Nozin. I'm a third-year PhD candidate here at the University of Padua. I'm interested in network and distributed system security, and I'm going today to present Updaticator, which is work done in collaboration with Darmstadt and the Intel Collaborative Research Group in Darmstadt. So this is actually work that we I presented in 2014 at the SWIX conference in Poland. And this is basically the outline of my presentation. I will give you some motivation about the work, and then I will dive into the contribution-related work, and I will briefly describe my proposal, our proposal, which is Updaticator, and then present a little briefly evaluation and the conclusions. So the work deals with software updates distribution, and so let's see here. This is the scenario. So we have a bunch of devices that needs to be updated by a software provider, and in the case in which we have just a bunch of devices and just one software provider, then the task is easy. The software provider can simply software updates to the devices, and everyone is happy. However, then we are seeing a growing number of devices is populating the world, and this is sometimes referred to as the Internet of Things. So we have plenty of devices, big or tiny devices, everywhere. So everyone will have a smart fridge in 5 years probably, or even in less time. So we have a high diversity in the devices that are connected to the internet, and then the needs software updates. And this clearly creates a scalability problem, especially if we have multiple software providers that needs to distribute updates for application installed on all different type of devices. So in this scenario, clearly scalability is a major issue. So to improve the scalability, typically software providers rely on trusted third-party distribution networks. For example, content delivery networks such as Akamai, to help in the distribution of these software updates. And typically the model is that the distribution network is trusted. So the software provider fully trusts the distribution network, and the distribution network applies some request aggregation and intelligent caching to be able to aid the distribution of the software updates. Well, this is actually the scenario that we consider, because there are many cases in which the software provider does not want to trust the distribution network. So we may have, or we envision like general purpose distribution networks, or like cache-enabled networks. So pieces of the network that actually perform caching, purposive caching, distributed caching, and request aggregation not for special purpose applications. So not like content delivery network that are with which software provider make sign contracts, but general purpose. And this actually was motivated by the recent trend in the content-centric scenario, where in networks where we are moving request aggregation and caching at the network level in future internet architectures. So when we talk about security software updates, we have to think about security, of course, and we have to think about the security of devices. So this is basically what happens. This is the windows of exposure. So it's the time that goes from when a vulnerability is introduced and the patch is delivered, right? So in our work, we wanted to minimize the time that goes from that start when the patch is released and when the patch is delivered and installed into the devices. So that's actually the red part is the part of the window of exposure that we want to minimize in this work. And this actually has a high impact in the time the device is exposed to potential attacks. and it can be actually patched by some software update. So what I want to do in this work is to provide a software update distribution protocol that can allow fast delivery and potentially scalability to the billions of devices, that can guarantee the confidentiality of the software updates and want to prevent devices from accessing updates that are not intended for them. So you can imagine not only security updates, but also some premium updates, for example, maps for GPS and so on. And want to prevent network attackers from accessing this confidential attacker. So we have two different attackers. So we have an external attacker who can eavesdrop, for example, the traffic, who can listen to the traffic, and we don't want him to be able to access the software updates. And we don't want other devices that are still legitimate devices, but for which the software updates were not intended. So as a third requirement, we want to have, of course, authenticity and integrity of updates, and we want to allow the devices to be able to verify the origin of the update and its integrity. We want to guarantee update freshness, so in a caching context, the device must have a way to make sure that the software update he downloaded is actually fresh, so it's like the most recent one. And then we want something that is cheap and easy deployable. So it was something simple and cheap and easy to deploy, with potentially reusing existing infrastructures. So we propose Update Indicator. It's a very fancy name for our protocol, and it's a protocol for some confidential updates when we are in presence of untrusted cache-enabled networks. So in presence of these distribution networks that apply caching and request aggregation and that are untrusted. So an example is named data networking, which is a feature architecture that has been proposed and that performs this caching at the network layer. And actually, this was what originates our idea, basically. So what does Update Indicator do? Cacheable update selection and download from devices, so devices can select and update them and select the available update. And actually, this distribution is cacheable. Can reduce the average content interval time, so we are much faster in the distribution of software updates, and that is very and increases scalability of the system. And it actually responds to the requirements for confidential update distribution systems that we highlighted before. And finally, we have implemented, updated, and evaluated the protocol on top of named data networking. Details about named data networking, sorry, I will refer to NDN from now on. But I think it's not really essential for this presentation. So these are some example of real-world software update distribution. So for example, Apple relies on Akamai on the delivery network, and then you can use HTTPS, so it establishes secure channels with the server, and actually with Akamai. And Linux updates and that use apt-get for authenticating software packages, but we then go into the node for HTTP, and we have still pairwise channels, one-to-one channels, secure channels with Microsoft updates, and then there is the protocol from on the Open Mobile Alliance for the digital right management. So we wanted to maintain the confidentiality of the updates, and so we have so typically what's going on is that we establish secure communication channels between the device and the update source, or the content delivery network. But in a case in which we have a non-trusted content delivery network, this may create a bottleneck in the distribution performance. So what we want to do instead is to have a way to, so we have to encrypt the software updates, the patch with a symmetric key K, and then distribute the key separately, of course. So we want to distribute the software update encrypted for everyone that wants to download it. In this way, it can be cached actually by the network, and we want to separately distribute the key. So this is what we want to do, and so we need a way to distribute the key, the symmetric key. We encrypt this software update with the symmetric key for efficiency reasons. We evaluated two possible cryptographic tools that were public key cryptographic tool. Of course, in this case, you want to use public key cryptography. And we actually evaluate broadcast encryption and CPAB, which stands for Ciphertext Policy Attribute Encryption, which are two public key encryption mechanisms. In the broadcast encryption, one can actually encrypt some piece of content of data using some identity of the intended receivers, and especially you can actually encrypt some data for a population of devices, just specifying who are the revoked IDs, so who are the devices who are not who cannot decrypt this data. And this actually allows fine-grained device revocation. Well, with CPAB, you can actually encrypt the data not specifying identities, but specifying attributes. So you can actually distribute attributes to devices, to users, and you can actually specify which attributes the user should have in order to be able to decrypt. So it's a very high-level and powerful tool. And actually, we decided to use this one because it actually meets more heterogeneous scenario on a large scale. So you don't want to distribute the software and say, oh, who is gonna would be allowed to receive it. Much more scalable to specify who has the right attributes to download, because multiple devices may have the same attributes. So you can actually target much larger populations. So a bit more details on attribute-based encryption. So it's a public key encryption scheme where you have an authority who distributes keys. And basically, we have a master key which is kept by the authority, who is issuing secret keys to users, and a public key to everyone. And basically, what the data owner can do is basically define a Boolean policy, basically, such as, oh, everyone who is series 1, it's missing an S probably, series 1 model blah blah blah, can actually decrypt this this piece of data. And in this way, you can actually cryptographically enforce this access policy on the data and distribute it later. So only who has the right attributes who are specified inside the key can actually decrypt. So this is the way it works at a very high level. I'm not giving you much more details on that. But I will instead briefly describe how the protocol works. It's very simple. So we have a scenario where we have a distribution server, a policy server, an update server. So the policy server defines who can actually access the software update, and while the update server is the one who is in charge of distributing the update information, and then the distribution server is basically an entity who is in charge of simply distributing the update. So like who the device that have to contact to download the update, actual update. So the first phase of the protocol is called update publication. We have the policy server has the updates, the new update released, and then simply applies an access policy on the update. So what this means, it means that it creates a random secret key, a symmetric key, then encrypts the software update with this key, and then encrypts the key with CPAB, specifying the attributes the device that should have in order to be able to access the key, right? And then it split this information in two, so it gives the encrypted symmetric key to the update server, while the software update to the distribution server. So we have a second phase, which is update selection. In update selection, so the device wants to check for updates. So it's like a pool-based model, and the device simply asks, "Oh, by the way, is there any update available to the update server?" So the request is forwarded to the update server, and what happens to the update server says yes, there is some updates, and then updates are delivered to the device. So I'm referring to this phone here. And what happens is that the network says, well, just to be sure, I will cache this update for you, so that if we have other devices requesting the same update, this is actually it's an update information. Sorry, it's not really update, not yet at least. So we have the devices are simply served directly by the distribution. This is what simply happens when you are having any cache enabled or distribution. And finally, the update retrieval. So when devices download this information, which is like a small piece, a bunch of information, this information contains let's say for example, a hash of the software updates in such a way that the devices can later on retrieve the update. So this is actually done because in the previous phase, so in the update selection phase, compatible devices will download the same update information, while in the last phase, all the devices that can actually download the same update will be served by the network. So it's important to maximize the chance that the network will cache and that the device will retrieve the information from the cache. So in this case, simply the first requests are served directly by the distribution server, while subsequent requests would be just served by the distribution. So here is some evaluation to show that this actually makes some sense. And this is actually the network topology that we consider for our test. We used as network simulators for this. We use NDNX, which is a early version of the main data networking protocol that we were using as a TCP overlay, so running on top of IP, TCP IP. And then we used the NS3 network simulation plus direct cross execution plugin. And we connected to this network where you see this rows here, gray numbers here. We connected from 100 to 900 clients that were actually requesting updates. And we consider a very big software update of 1 megabyte, and we make the devices generate bursts of requests in a time window of 30 seconds. Just to simulate the worst case scenario. And it's actually the results of our evaluation. This is basically we tested HTTP download for this. So to mimic secure channels with the source, basically. So this is surprisingly the way the growth of the. So this is actually in log scale. So it's it's in log scale, and this should grow linearly, and this grows logarithmically. So this grows logarithmically and basically almost it's actually constant. Sorry, and it actually grows linearly in the number of devices. And this is actually the transmission data from the server point of view. So the devices are requesting this software updates, and this is actually how much the software update source has to transmit in order to serve all the requests. And this is actually the amount is have to transmit when we are not using hardware mechanism. And this actually is the time it takes to retrieve and download to download the software update. And as you can see, it remains constant almost for all the devices. This is an average for all the devices that were connected to the network. And you can see how it grows when we are not we are just using channels, secure channels with the source. These are some benchmarking of the use of CPAB on a common laptop. Typically, when you use this, the more powerful the crypto is, the more expensive in terms of computation. We see that basically it's not really comparable with RSA because it really depends on how complex the access policies are, but still manageable. So this is just to give some numbers. So to conclude, we've designed Subdedicator, which is a protocol for large-scale distribution of software updates. And the protocol is intentionally simple. we didn't want to provide anything too complicated, because our aim was to provide something that was able to work in the real world and people were willing to use, and that's therefore we designed it to be simple, to work, and actually to work also with unmodified infrastructures. Distribution, and but maintains also it allows to download a software update securely. And it's actually some future work. If you have any question, if you're interested, and want to have some sort of introduce some sort of optimization for local networks and for more resource-constrained devices, we actually did some work to verify the possibility to use this more expensive cryptographic tool on resource-constrained devices. And we show that to some extent it is possible. And another potential future goal is to coordinate updates to maintain compatibility among devices. So assume you have a group of devices, you want to update a large group of devices, but you have to maintain a heterogeneous device that needs to cooperate, and you don't want to update some device, like sometimes happens, and then you install, for example, a new version of a protocol, and then it's not compatible anymore. So you want to have some sort of transitional updates over a large population. And this is actually some real nice future work that we are considering. And finally, a big deal with the CPAD is to have revocation and traceability of devices. So in this case, as you distribute to a large population, it's very hard to trace who do some trade-on tracing. So. But it's actually a very hard problem, and we are still trying to think a bit more about that. So thank you very much for your attention, and if you have any questions.
I have a question, maybe related to your last point in related work. Would it be possible with this scheme for clients to spoof attributes in order to obtain some content that they shouldn't be supposed to, since it's a part of the encryption key?
So yeah, you can certainly spoof attributes, but in order to be able to access the content, you need a private key that actually matches these attributes. So you really need a private key in order to be able to decrypt. So even if you know the attributes, you really need a public key issued by the authority to be able to decrypt. So that's not really not possible. This may be a privacy issue. If you can spoof like a request and say, oh, these are the attributes of the device, then you may know what are the attributes of a device. But attributes that we envision is like model number, CPU, RAM, and blah blah. So it's really, if you go like for a smartphone, you go online and check the specs. It's not really privacy.
You just know the type of device is there.
Yeah, so it's not really a secret.
Might.
But it might be. It depends on.
You might know vulnerabilities.
Yeah.
Any questions? Can you maybe tell us something more on the feasibility of AD?
Yeah.
Devices in general.
So basically, AD-based encryption is a expensive scheme, and usually in implementation use pairing-based cryptography, which is expensive. So what we have done is we ask ourselves, okay, when we have this protocol that works, the chances that I'm using it in more resource-constrained devices than my laptop. So in my laptop, you don't even notice the difference between this and RSA. But as you increase the number of attributes, as you increase the security, you have several performance penalties. So what we have done is just to adapt some existing code for CPAD to more resource-constrained devices and actually perform some benchmarks in order to derive some sort of, let's say, boundaries, and in order to allow designers and developers to immediately check whether this a certain range of attributes or certain complexity of the policies that you want to enforce at the application level, actually how much they they can actually impact on the overall performance. So actually, it is feasible to use it or not based on the application constraints. And we have made some tests on IoT boards like Galileo, Raspberry Pi, so very cheap and common development boards.
Is the code available?
Is the code will be available soon, very soon.
Thank you. No other questions?
No.
Hello, I'm Riccardo Spolaor, a PhD student in Brain Mind and Computer Science here at the University of Padua. And my talk is about the user privacy threat on mobile devices through encrypted network traffic analysis. So, as an overview of this presentation, I will talk about encrypted traffic analysis. And first of all, I will introduce our work about user action recognition, and then we move on mobile app recognition. The first work was published in CodaSpy in 2015. It was a work in collaboration with the University of Padua and Sapienza University of Rome. And then the second work about the mobile app recognition has been done in collaboration with the University of Oxford. So many researchers highlighted that encryption is not enough to hide information. In fact, Song and Toll in 2011 was able to infer the keystroke of the SSH channel in order to recover passwords, to infer passwords, and also over IP. If I continuously repeat the same phrase, I am able to recognize it, even if encrypted. So our scenario is this. In practice, we assume we have a man-in-the-middle attack where the listener is between the device and the web service. And what we are able to see is just encrypted traffic, so the payload inspection is not feasible. And from our observation, we are able to see the packet length, the packet direction, and the timing. But we don't know, we don't rely too much on timing, but only the order of packets, because the timing can be affected by the quality of the network. So from this information, we are able to do some traffic analysis. So the goal of Can't You Hear Me Knocking, that is the first work I'm going to present, is to infer private information about the user, in particular about the user action the user is performing with a mobile app and just using the encrypted network traffic. So let's assume we have a user with his encrypted traffic and another user in Facebook that wants to remain anonymous. So from the first user, we are able to see, to log every user action is doing on Facebook. For example, at that specific time, he posts something on his wall, and so then a private message, then another post, and so on. And we're able to see that in the anonymous account, we're able to see all the posts and the message and the post on other walls. And then if we can correlate this information to the time, then we are able to de-anonymize the user. Okay, this was the first scenario. But then
If I know the network traffic about the user and an attacker wants to retrieve his password, then we will be able to see which portion of traffic corresponds to which action. Just focus on the one we are interested in and do some brute force attacks and in order to recover the information we want. So, other possible attack are if I'm able to see the user A send some message and the user B at the same time receive that message. After a lot of message, we are able to finally correlate these two users and discover that there is a relationship between them. But also, if I have, for example, a McDonald's hotspot that provide free internet access to all the customers, we are able to see which action the customer do in order to gain some marketing knowledge and invest more on Facebook or rather than on Twitter to advise our McDonald's products. So this is another scenario. So some definition, first of all, we are not aiming to discover the interaction with the phone. In fact, the interaction are just tap, swipe, and key press on the phone. But we aim to discover the user actions that are, for example, sending an email, open a web page on Facebook, or send a tweet. And all those user actions do some network traffic. And network flow, we consider as a network flow a sequence of packets that share the same couple of IP addresses and ports. So these were some definitions. In first instance, we were able to see that network flow had a shape. As we can see, we have three different flows that assume three different shapes. This was an idea to start with in order to see that we can discriminate flows and we can identify some set of flows according to their similarity. But in our analysis, we consider flows as a time series of ongoing and incoming packets that are marked with plus or minus, depends on the direction of packets and the size of the packets. So we used a machine learning technique in order to first train our framework and then test its performance. And first of all, we did some network traffic preprocessing. So we filtered out all the errors and packet repetition and so on. Sorry. Then we fed the machine learning classifier. In this particular case, is a random forest algorithm in order to get prediction on a test set, and to be sure that our classifier works well. So these are some preliminary results on validation set in order to tune the number of cluster parameter. And as we can see, we are able to see which number of cluster is the best one in order to obtain an accuracy, a higher accuracy. So after tuning this parameter, we were able to retrieve the actions. And on our test set, we were able to achieve very high accuracy. For example, for Facebook, we are above the 95% for almost all the actions. And the same for all the other applications considered. For example, we consider Facebook, Gmail, Twitter, Tumblr, Dropbox, Google Plus, and Evernote. The only action that we were not able to classify correctly was the open chat, but now, fortunately, this function in Gmail was deprecated. So, with this work, we were able to demonstrate that encryption couldn't hide the communication pattern. In fact, we are able to see user actions on the traffic. And then with this information, we are able to undermine the user privacy and learn about his habits and gain some commercial insight. And since we are talking about mobile devices and mobile app, we are still working on countermeasures that are not so easy to be deployed. In the first work, we say, okay, we have to see if this traffic belongs to Twitter or this traffic belongs to Facebook. And in order to do so, we relied on NDS lookup, because we assumed that, okay, if I'm communicating with Facebook, I'm talking directly with the Facebook server. But this is not the case anymore. In fact, this is not always feasible. And the second work, called App Scanner, as this goal has to identify a mobile app according to the encrypted network traffic it generates. But, as I said before, this is not easy. In fact, first of all, since the packets are encrypted, we cannot do a payload inspection. And second, usually, in the past, usually the owner of the IP address was the service provider, but it's not like this anymore, since there are proxy and content delivery network. So this was the traditional scenario where all the users and the mobile apps were talking directly with the web provider and with the web service, for example, Gmail, Twitter, and Facebook. But right now the situation is this. So we are not able to talk directly with the server, but in the middle there is some content delivery network that provide the contents for instead of the web service. For example, the services deployed by Akamai, Amazon, and Oracle. So we want to be able to recognize the app from the network traffic. So what are the scenarios of this in which we can rely on about this information? The first scenario is knowing that in a specific mobile device of a user, there is a specific app, for example, the app X, and we know that in the app X there is some vulnerability. We can attack that user. But also, knowing from the network and administrator perspective, we can notify the user that in his device there is an application that is vulnerable. Then a second scenario, as reported in this work from Mohapatra, if I know the exact set of applications installed inside a device, I can learn some information about the user, and quite sensitive information. For example, his age, his sex, religion, relationship, and also the country of the user. Finally, the third scenario is from the network administrator point of view. And if I want to know which kind of application is installed on a phone and allow my employees to bring their device with for example, allowing Facebook only on specific hours a day, or not allowing at all, I can use this framework in order to infer the presence or not of Facebook inside the phone. But then we can also do some quality of service improvement in a network in order to allow some application rather than the others. So in the paper we published in EuroSMP 2016, we proposed 3 different methods. And the first one is per flow length classification that we will see in detail later. But this method is very fast, but is not resilient to out of order packets. In order to cope with this weakness, we came up with a large multi-class classifier, so a huge classifier that is able to detect a huge set of apps. And this provides a high accuracy and is not resilient to out-of-order packets, but at the same time is quite slow in terms of training, since we consider a huge amount of data. But then, if we are interested only in a single specific app, we can use the per app classification. So it involves a binary classification where we can say at the end as a prediction, okay, is the app X or is not the app X installed on the device? And it's quite fast. So the data we rely on is, again, the encrypted network traffic. So we have the IP destination and the IP source, the protocol, and the length of the packets and the precise order of packets. And then for the per flow method, we just filter out all the errors and repetition packets, and we consider as the data set the time series as it is. But then, in the other two methods, we first extract some statistical feature, for example, the mean, the standard deviation, the variance, etc., about the time series. Then we scale everything from 0 to 1 in order to have the classifier. And finally, in order to cope with the curse of dimensionality, we select only the relevant features. And then we obtain we obtain feature vectors with the same lengths. Things that we don't consider in the first approach. And then we're able to perform the classification and the testing. So these are our results. Per flow classification is good, but not so good, since we achieve an 82% of accuracy. But the single large classifier, when we achieve 87% of accuracy with the random forest, that is not bad. From SVM, we achieve a very, very low accuracy. So in this case, random forest performed well. But paired up classification, since it's binary classification and we are just focusing on a single app, the accuracy is very, very high, almost 100%. But then we have to improve. Since we want to know from a set of application which of them are installed, we have to improve this accuracy here. And in order to do so, we exploit a property of the classifiers. In practice, when a classifier gives you a prediction, it doesn't give you only the prediction, but gives also the probability of that prediction. In fact, this probability is to, for the classifier, is to say, okay, I'm very sure about my prediction, or I'm a bit uncertain about that prediction. And rely on this fact, we use a probability threshold in order to filter out all the flows with a prediction that is not very that is not satisfying. And we did that, and as we can see, we were able to improve the classification of per flow, the first approach, per flow classification, almost 95%, and the same with the large classifier, with an accuracy almost on 99%. Okay, but since we are filtering out all the flows that we are not certain about them, we are still filtering out flows, and in order to obtain such accuracy, such high accuracy, we have to discard the 25% of flows. That is not a big deal, since since every prediction is on a single flow, and during the usage, an application sends a lot of flows. So about some comparison with our competitors, that okay, they are not meant to do this kind of classification, since they just focus on web page fingerprinting. Almost every classifier that we are proposing has an accuracy higher than our competitors. In particular, the highest accuracy of our competitor is 64%, while our is 71%. So thank you for your attention. If you have any question. Yes?
You were talking about man-in-the-middle situation, but can this approach be using with wireless encrypted packet?
Wireless, you mean layer 2?
Yes. So you have only to sniff packets without.
Okay, there are works in this direction, but after a lot of discussion with my colleagues in Oxford, we studied that work very well, and we came with realizing that it's not feasible to distinguish flows. In fact, since, for example, Android is a concurrent system that relies on threads, if we don't know the IP destination and the IP source, okay, actually only the destination, we are not able to discriminate flows. And so it can happen that an application sends a flow, and at the same time, another application sends another flow. These two flows, while you are on layer 3, you are able to distinguish them. But if you are on layer 2, it's impossible to distinguish them. And you cannot foresee every possible intersections. And in that case, you are not able to discriminate them, and that approach is not working. In fact, in that work, I don't remember precisely, maybe I had it. No. No, no, okay. The second work. Yes, the second work done by Wang was relying on layer 2, but they have a very, very a strict conditions in order to collect data, because they have to be sure that no other application was running and sending packets. Instead, they have collision, and in that case, they are not able to infer the app anymore. Okay. I hope I answer your questions. Yes. Okay. Thank you. Online questions?
Questions? No.
Okay.
Thanks again.
Thank you.
I would suggest we take 5 minutes break, maybe coffee, and come back. Maybe you can stop the
Okay, after a break, we are continuing with the presentation. Now is the turn of Daniele Lain with Don't Skype anytime.
Okay, good morning everybody. My name is Daniele Lain. I'm a research fellow here at the University of Padova. This work is called Don't Skype and Type, Acoustic Eavesdropping in Voice over IP. This is actually a technical report. It's from my master thesis, and it's a joint work with Alberto Compagno from Sapienza University of Rome, Mauro Conti, my advisor here in Padova, and Jean Zunic from UCI Irvine. You can find his work on arXiv, as I said. So, this is the outline of my talk today. We're going to talk about physical emanations of electronic devices because they open up a big class of problems, which is the eavesdropping of these emanations. And we're going to talk in detail of the keyboard acoustic eavesdropping problem. We're going to design an attack on this, which is going to work over Skype. We will show the setup of this attack, which is an attack that allows someone to recover the keystrokes that the remote party is doing during a call. We evaluate the attack and we give some practical details of the relevance of this attack, and then we will draw some conclusions and propose some future work. So, the problem of physical emanation is that nowadays we use electronic devices like this, we use them every day, and while they are doing their work for us, they have some emanations. They could be electromagnetic emanations, for example, they have wireless transmission, data transmission. They can be optical emanations, such as the monitor of the device, reflections of the monitor of smartphones, for example. They can be acoustic emanations, such as hardware sounds, of course, the keyboard, but also the CPU working gives us some information of what's happening inside it because of the sound of the hardware. And they can be movement emanations, for example, when you interact with smartphone devices or other handheld devices. And the problem with these emanations is that they can be eavesdropped by someone, and the big problem is that this someone can be malicious, of course. So, eavesdropping is convenient for the malicious party because it's a convenient means to steal sensitive data. Basically, it often allows someone to place himself like if he were in the back of the user. For example, if someone is typing something on some protected channel over the internet, by eavesdropping what he's doing on the keyboard, we are not anymore in the middle of the network, which is protected by encryption, but basically we are just looking at what he's typing, and this is unencrypted and unprotected, thus disrupting any other security implementation that can be in place to protect the user. And we can eavesdrop in many, many different points nowadays. We can do it in the transmitting medium, for example, in network cables, in wireless emanations, in peripheral buses on the motherboard. We can do it for input and output devices, such as keyboards, touchscreens, monitors and printers as well, because they have emanations that can be exploited. We can do it on processing mediums, for example, CPUs, hard drive sounds, hard drive content, of course, and RAM. Big problem we're going to look at today is the keyboard acoustic eavesdropping, which is an attack that can be summarized as such. We have a computer, it can be a normal computer, a laptop computer. The user is typing something. The keyboard, of course, makes some sound because when we press the keys, they all have some sound. This sound gets picked up by some microphone controlled by the attacker that retrieves the sound and then applies some machine learning algorithms, some processing algorithms in order to retrieve the target text, which is, of course, a password in this case. It was done in the past by some other research efforts with supervised learning techniques that have small input assumptions because the input can be password, English text, any language text, but of course it's more specific because it needs training on the specific user and specific machine that you want to attack. And it was done also with unsupervised learning techniques that have more input assumptions, such as the word needs to be from a dictionary, the word that the text needs to be in English, for example, but they are more general in the sense that they can attack more computers and more users without specific training. Nowadays, researchers also exploited mobile phones and multiple microphones in order to use new techniques. As we can see here, if you use for example, mobile phones that have two microphones, one each, let's say, you can retrieve the sound of the key, and without using the sound, you can use the timing, and by using the timing information, the different time of arrival to the devices, you can do some triangulation, and you can infer the position on the keyboard where the key was pressed, and then if you know the layout or if you guess the layout, you can understand again the password from the sound. And this is of course completely context-free because you don't need to know anything about the laptop or the user, but it's more difficult to set up because you need some physical proximity, of course. So there are some difficulties with those attacks that are proposed in the literature. First of all, you need to trade off between precise training data, and it's not clear how you should obtain precise training data, or you can use general training data or no training data at all, but you need a lot of data, of course, for example, to do clustering of letters, to then use the frequency of the different letters and retrieve some oops text. What happened? Okay. And or it needs to be in a known language, for example, you cannot use passwords. And moreover, you need physical access to perform all these attacks, which is an unrealistic scenario, we argue, because you need to place microphones or cell phones in the same room or at least near the target device, which is not realistic because then, of course, if you have physical access, you can do way worse than just putting a microphone on the room. So, our proposal is to use voice over IP software, which is one of the most used software every day for many users. For example, Skype has many millions of users, and every day they spend a lot of time doing Skype calls. And what can happen during those Skype calls? It might happen to type private stuff while I'm talking with someone. I'm talking with someone, and maybe in the meantime, I log into some website, to my Gmail. I write a sensitive email where I say that the other part of the conversation is boring, and I want just to quit the call. Any other sensitive information, of course. And the other party, of course, can eavesdrop the sound of the keys during the call, because as you can see here, if this is the victim, he types something, and as in the same scenario as before, the microphone willingly actually takes up the sound of the keyboard of the victim and transmits it to the attacker, which is not us now, over Skype, over the internet, and then I can use that sound to eavesdrop on the guy. So we can design an attack on this, we can try to recover what he's typing, so we can see that he hates us, as I told before. And now I'm going to show you how we design this attack and the setup of it. So this is the general flow of the attack. We have the victim here, and he's going to input, let's say, a short random password. This is a worst case because, of course, if he's typing in some known language, if he's typing meaningful words, we can use some techniques to improve the accuracy of our attack. Of course, if the input text is short and random, this is some kind of worst case. So if you're able to do this, we can do it with more precision if the text is English, if the word is meaningful. So the microphone picks up the sound, it transmits it over the internet to us. We receive it, and then we record it with some software. And then we have the sound, we process it somehow, and then a number of scenarios can happen depending on whether we know what laptop he's using or not. If we know what laptop he's using, we can just use some training data that we already acquired or that we are acquiring during the call, and then we can classify the keys. Otherwise, we need first to classify the laptop to understand what laptop he's using according just to the acoustic information that the keyboard gives us, and then we can proceed to classify the keys. With the goal, of course, of understanding this password. We're going to see all these scenarios later in detail. For now, we need to answer some questions. I will just outline them here quickly. What tools to use for the attack? Is it working consistently, meaning that there should be no big difference between different laptops, different users, different typing styles, for example? Is it feasible in the real world, since this is a very practical attack? And maybe using VoIP poses us some additional challenges, because of course that's the quality of the call to consider, that we know can change a lot according on whether there's big bandwidth, internet bandwidth, or small internet bandwidth. And of course it's a call, so maybe I'm typing and I'm talking on top of it, and the voice can disrupt this keyboard information. So for the first steps of the attack, This is what we receive actually, so we receive a waveform, and we need to set up some system to automatically extract the key sounds. Fortunately, keystrokes have a very distinctive pattern that we can see there, where we have a hit peak and a release peak that correspond to when we first touch the key and go all down, and then when we release the finger. And it always produces this kind of pattern that we can individuate, and if there's a silence around, we can use some threshold on the energy of the different time intervals, and when we pass some threshold, we can extract a short portion of the waveform and extract this way the sound samples of the key. And then we need to extract some features. We selected this feature, which is net frequency capture coefficient. It's a known transformation of the sound, and with some preliminary experiments, we determined that it gives us the higher accuracy. It's better than normal capture and than faster Fourier transform. And then in order to use this information, we use supervised learning techniques. This is because since we assume the target text to be short, we cannot use the unsupervised learning techniques such as clustering big amounts of data. And since this is random, we cannot use constraints. We cannot do some predictions on what we expect the data to contain. For example, many A's and E's rather than Z's, of course. So we cannot say it. And to classify the keys, we use the machine learning technique. It's a linear technique for logistic regression because it gives us the best performance. And we're going to evaluate our attack using this metric, which is top n accuracy. It means is the correct character within the n most probable characters that our classifier predicts. And we can see we are going to report the results as a function of the top n accuracy, as a function of the number of guesses, of course. So we can see the first result is the top 1 accuracy, so the normal accuracy. In the middle, we have the top 5 accuracy, meaning that he is the correct character within the 5 most probable characters. And we're going to focus especially on the top 5 accuracy because of practical reasons. We are going now to evaluate this attack that I just detailed to you. To do that, we collected the data from 5 different users. The data was 10 repetitions of the keys from A to Z, so the English alphabet, on 3 pairs of common laptop models from all the users, using 2 different tagging styles. One is the idealistic hunt and peck style, where you use just your index right index finger for all the keys, and the other scenario called touch typing in literature, we used all the fingers to press the keys in order to evaluate different angles of impact of the key on the keyboard and different strength, of course, of typing. And with all this data, we then filtered it through Skype because it's the most popular VoIP software, and we are going to attack it, basically. And the subsequent experiments, we're going to evaluate, as I said, the top 1 and top 5 accuracy of character recognition against a baseline based on my a download random guess, because since it's a random password, we cannot use smarter approaches that exploit letter frequencies, also for the baseline, of course. So one of the novel parts of our work is to evaluate the attack on 3 different realistic scenarios. The first one corresponds to the common scenario in the literature, for example, in the works of Azonov and Alevi. We call it a complete profiling scenario, because we profiled the victim on his laptop. So we have a specific training set tailored on that user on his laptop, the laptop that we are going to attack. This can happen if we have some ground truth disclosure. For example, we are talking over Skype, and the victim sends me a short chat message. Of course, I hear the sound of the keys. I can read the chat message because it was sent to me. I can label some data with the correct labels, and I can build a specific training set on the user. The other 2 scenarios are slightly more difficult. The first one and the second one we call the user profiling scenario, because we profile the user, but on a different laptop of the same brand, for example. This can happen through social engineering techniques. The assumption behind this is that you usually Skype with known people, so you can probably obtain some information, for example, giving him some other laptop and having him do stuff on that and recording him in order to understand whether the user makes a big impact on the attack. The last attack is the most interesting one. It's called the model profiling scenario, where we profile a laptop of the same model of the target laptop that the victim is going to use, but we profile it on some completely different users. For example, a crowd of attackers that all train our system on, let's say, the MacBook Pro, this model, and then we know that our victim is going to use a computer of the same model, but of course a different computer. And the victim can be completely unknown to us, and so basically we never seen his computer and his typing style. And we are going to understand what computer he's using and then, of course, to attack him. So the complete profiling scenario, so the most convenient one for the attacker, where we train with the data the user disclosed and then attack. We can see we tried two different combinations. The best one, where we used the unrealistic typing style, and we didn't filter the data out of Skype, so basically this corresponded to the literature. We can see that we can obtain an average top 1 accuracy of about 75, almost 80%, and the top 5 accuracy, which is very high, more than 90% on average. But the interesting part for our work is that if we use touch typing, so the realistic way to type something on a keyboard, and we use Skype, so basically we perform our attack, we can get basically the same results. So we didn't find any impact from the typing style, and more importantly, we didn't find any difference from the sound, whether it was a clear recording or it was filtered through Skype. So we're going to further evaluate only the realistic combination of touch typing and, of course, filtered on Skype, because the attack is meant to be through VoIP. And as we can see in the complete profiling scenario, we can actually attack the user with a very high accuracy, both the top 1 and the top 5 accuracy. One observation that can happen in this scenario is that, of course, if you remember it correctly, we trained the system with 9 occurrences of the letter A, 9 occurrences of the letter R, 9 occurrences of every letter, basically, which is not your typical chat message, because we cannot expect it to be composed by all the letters uniformly. So what we did is to create a training set with realistic letter frequencies. So basically we took our training test and we started dropping the samples according to the letter frequency of, let's say, the English alphabet. So this is what I can expect to receive on a chat message. And then using this training set, we tested it again against random passwords. We can see that we suffer a small reduction on the accuracy in the order of 15% on average, both on the top end guesses, but we're still very successful. In particular, we can get as high as 70% almost on top 5 accuracy. So we suffer a small decrease on accuracy, but if there's even a small disclosure of ground truth in the order of 100 characters, so a typical chat message or a typical tweet, we are able to successfully attack the victim over Skype. On the other scenarios, this is the user profiling scenario, where we somehow profile the victim on a different laptop, but of the same model. We can see that the accuracy starts to go down, but we still have some alarming 40% on average accuracy on the top 5 guesses. And on the most interesting scenario, which is the model profiling scenario, we have a number of additional challenges. First of all, the victim can be unknown. And even if he is known, we first need to understand what laptop is the remote party using. So the first step is to understand it. And to do that, we try to match it with a database of model signatures, so just model, but of course different laptops. And we found out that we can guess correctly 93% of the times the laptop model, if the laptop model is known. If it is not known, we can use some statistical measures to determine that we don't have that model and we need to postpone the attack for when we will acquire that training data for that model. And this is the scenario, these are the results, so we can see. If we take this laptop of the same model and just the attacker trains our system, and then tries to attack someone, we can see that we are still better than the baseline random guess, but the numbers start to go down to, well, we are about twice as better than the random guess, which can be not so satisfactory. This shows that there's still some acoustic information related to the model that gets transmitted and that is still present because we are able to understand something. But one convenient way to increase those numbers is to use a crowd of multiple users. So basically, what we did was to train on the laptop of the same model of the victim one 4 users instead of 1. And by doing that, we can see that we can get, on average, on more than 40% top 5 accuracy, which is way better than the random guess, of course, and which can recover somehow the attack to reasonable some practical details now of this attack that I just presented to you. First of all, of course, we talked about understanding passwords. So, are we good in password cracking? Yes, there's a good speed up to brute force techniques if we use different techniques according to whether we are accurate or not. So, if we are very accurate, such in the first scenario, we can have a great password entropy reduction because on average we guess almost all the characters. If we are less accurate, let's say 40–45% top 5 accuracy, of course, we cannot just guess the password. We need to employ some intelligent brute force algorithm where we try first all the predictions that the classifier gave us. So we can exploit the confidence basically of the predictions and then try the other letters. By doing that, we can obtain a good speed up on the brute force, on the normal brute force by exploiting this fact. And we can reduce the time needed to brute force a password by several orders of magnitude. Some other practical details that I'm not going to explain in too much detail are the volume-specific aspects that I talked to you before. We saw that our attack is robust to real-world conditions. For example, if the internet bandwidth is very, very small, down to as little as 30 kilobits per second, so a very small bandwidth, our attack is still robust because the acoustic information gets degraded, but since the signal is very complex, so what we learn is a combination of many, many frequencies. We can still understand most of it, and we suffer basically no reductions until the code is so bad that the users would probably stop it. And if someone is talking on top of the key presses, which is a very practical scenario, is what can actually happen on a call, until the voice is as loud as the sound of the keys, so very loud if we consider a laptop where the keyboard is enclosed with the microphone and the sound of the keys is very strong, we suffer no decrease at all. So when the voice starts to go higher than the sound of the keys, of course, there's a frequency masking phenomenon, so we can start to lose accuracy and we quickly start to lose it, but this means basically that the voice needs to be way stronger than the sound of the keys, which we argue is a bit difficult. So this calls for countermeasure, of course, and the first countermeasure is don't Skype and type, of course, and not sensitive information at least. But since we're more interested in restoring the functionality of something rather than just saying, oh, just don't type, we tried preliminary countermeasures. We thought that one could remove the volume when we detect a key press sound in a similar way as we attack. But of course, this impacts the voice because it just removes the volume completely, and this can cause damage. This can not be satisfactory for the user. What we can actually do is try to disrupt the spectral features that we learn on, of course, with some random equalization scheme. For example, we can pick at every time step, we can use some equalization, we can pick some random bands, we can just move them up and down by some random value and filter it, and then change it continuously in order to avoid the attacker to learn the scheme that we are using. And we implemented it, and we can see the results there. So we tried it both on the state-of-the-art works that we relate to, that are labeled with the fast Fourier transform. We can see that before the countermeasure, the green line is a very high accuracy, and after the countermeasure, we basically reduce it to the random guess, so our countermeasure is able to completely disrupt the other attacks. For our attack, unfortunately, you can see our red line is the attack, and our blue line is the attack after the countermeasure. So we are able to somehow disrupt it, but we'll still need to improve it, because the attack is very robust, even to this random equalization scheme. And of course, we need to assess the impact on voice to be sure that it doesn't change the perception of the other party in order not to disrupt the call, and to understand whether this is really feasible in real time during a call on a normal computer. So to conclude, VoIP keyboard acoustic eavesdropping is a serious threat because it's very robust, it's feasible, it's accurate. We saw that we can go more than 90% precision on complete profiling scenarios, so the normal one, and we are slightly better than the state of the art. And we can go as high as 42% on the model profiling scenario, which is the most difficult one, which is novel, and it is against an unknown victim. And it's very robust, both to degradation of the sound and to voice on top of it. As a future work, we are planning to use more users, more laptops, and more voice software, such as Google Hangouts, for example. We're going to try to attack another laptop in the same room, so attacking someone who is close, but it is not the party of the call. And we want to analyze and improve the countermeasures to see whether we can prevent our attack. Those are some references. This is what would actually happen if we need to steal the password, because it's faster. And thank you if there's any question.
It's interesting because it is interesting also for this scenario. Now we are transmitting on YouTube. The video of YouTube will be available also in future days if we are not removing. It can be. Is it really possible to think that we can, maybe knowing the laptop? I don't know if on YouTube we can see the model of the laptop we are using to record, etc. But do you think it's possible having this knowledge to train a general classifier independent from the user, so that, okay, we can take a video, a stream video, and perform some analysis to see if the person recording the stream typed something and then on somewhere else, maybe not necessarily on the chat of the video, but maybe it has Skype, it has, or it has a web page, login, is logged in to Gmail. Do you think it's possible to retrieve what the type, such as passwords?
Okay, so basically the scenario is that now this computer is streaming the video,
Yes.
and you go there and you type something, right?
Yes.
And this will stay on YouTube. Basically this is our model profiling scenario. So the first step that we did, and we show it's possible, if we have a database of computer sound signatures, we can understand that we are using this Lenovo, let's say. And given the model that we can understand, I can train the correct training data recorded by multiple users on a model of the same model of this device, and I can attack you with the last results. So basically, with this accuracy, as of now, on average. So yes, I'd say it's possible. So.
Okay, so don't type and then during live streaming on YouTube.
Yeah, probably. Don't type and transmit the sound in general. Okay.
Okay.
The next one. Done.
Yeah.
You want to connect your laptop?
Does anyone need the mouse?
You need the mouse?
Last one. Good morning, everybody. My name is Chagan. I'm a research fellow in University of Padua, Department of Mathematics. Today I will give an overview about an EU project in which our group is working. The project is called Tagged Smart, which is smart tags-driven service platform for enabling ecosystems of connected objects. So here the main thing is the smart tags. We already have tags in the form of the barcodes, NFC tags, but they are not smart. Okay, so we are talking about the smart tags that will help to build an ecosystem of IoT objects, and each object is marked with, or you can say, tagged with these smart tags. So the main goal of the project is we use the smart printed tags that can be scanned using the smartphones that everybody has almost, and the scan data is then sent to the cloud, where it can be used to compose various services for the end user, and all this together will give you an IoT for mass market products. When we talk about the mass market products, we are talking about the products like a bottle of milk, a package of meat. Such products we are talking about when we talk about the mass market products. So we already have IoT ecosystems, for example, smart homes, even smart cities. But our aim is to go beyond it. That is, we want to tag every item that are used in our daily life by the users. So we are talking about the mass market products. Okay, so we have the mass market products, but do you know their story? What do you mean by do you know their story? It means when they are manufactured, from that time till they are in the shop for the purchasing. Or in this case, or in the case of this project, till now they are put in the recycle bin, or you can say in the bin. So the story of the product from the manufacturer unit until it is put in the recycle bin. So do you know their story? Of course, we don't know their story. We just purchase them from the retailer and we use them. What we can know about them, for example, we can know about them that what are the ingredients that are used to make this product, that we can see at the back of the product, or also we can see if it is embedded in the barcodes that are associated with the products. But we don't know anything about them, that how they are reached here, under what circumstances or under what environmental conditions they are reached from the manufacturing house to the retailer shop. So our aim, the project aim is to let them speak, let them tell their own story that starts from the manufacturing unit and that will end when they are put in the recycle bin after their use. So for example, at the manufacturing unit, there is a batch of, let's say, there are 10 cartons of an ice cream. So those cartons are sent from the manufacturing unit to the shop. And in the way this can happen, that some cartons are still preserved in the required environment and some are not. So these are preserved, but these are not. But when they all go to the retail store, they are same. You don't know the difference between these and these, because we don't have any story about these products. So the overall objective of the, is it working now?
Yes, I think so.
So the overall objective of the project is connected mass market products, as I said before. So these could be the mass market products, and we want to put a smart tag which has a unique identifier and that can report on their environmental conditions. So this is the layered architecture, or you can say this is the layered architecture in which the project will be working. At the top, we have the functional ink and printed NFCs to print the smart tags. So with the help of these, we print the smart tags, and then we put those smart tags on the products. And now those smart tags could be scanned, and the scanned information can be sent to the cloud platform with the help of crowdsourced readers. So the crowdsourced reader includes the consumers that buys and use those products. Then that information can be sent to the cloud services, and it can further use to provide additional services on top of the existing services. And ultimately, it will create an IoT for mass market domain. These are the partners in the project. So we have large industries like Unilever, Fuji, Siemens. Then we have small and medium SMEs like Dunet, Donde, VTT. Sorry, VTT is the research industry. And Trust, everything. Then we have end users like Unilever. Then we have research partners like Unity, University of Surrey, and VTT. So this is the set of partners that are working in this project. So here you can see an example of the smart tags and how they will react with respect to its surrounding environment. Suppose this is the tag, this is the invisible ink. When this tag is exposed to heat, light, or maybe humidity, this invisible ink will appear. So you know that the product that is marked with this tag is exposed to heat, light, or humidity. You don't even need to scan it. You can just say by looking the tag, because here the ink is disappeared, here it appeared. Or if the same product is also using the NFC printed tags, then you can also say, you can also have a unique identity for each product. In this case, we are not talking about the unique identities, but in this case, each product will have the unique identity. So you can track each product individually with the help of the functional ink and printed NFC. So this is the Target Smart context. At the lower level, we have the functional inks and NFC that are used to create the digital markers, that is the smart tags, which are then scanned by the smartphones or any other scanning device. So we are not talking about the dedicated device for the smart tags. We are saying that these tags can be scanned by the general purpose scanners, or even with the use of mobile phone. And who is going to use these? The crowd, the users. So the data sensed by these crowdsourced user is then sent to the cloud services, where it can be used to provide additional service to the end users. So what is the benefit of these smart tags to various, you can say, stakeholders in the stack? So what is the benefit for the manufacturers? They are able to control the product throughout the life cycle of the product, and they can create channel to communicate and interact directly with the consumer. When a consumer is scanning a product, the information that it scans along with the information of the consumer is sent back to the manufacturer. So in this way, the manufacturer can directly communicate with the end user who is using its product. So this is how it is beneficial for the manufacturer. He can keep track of the product and he can directly communicate with the end user. How it helps to the transport companies, they can get relevant information about the products and can ensure its right transportation. How it is beneficial for the retailers, again, same as the manufacturers, they can be betterly engaged with the consumers. They have the item level control now because the tags are put on each individual product. Actionable data to increase customer satisfaction and boost sales. Then how it is beneficial for consumers, they get to know the story of the product. Now this is an example. Let's say we have an aspirin and a smart tag on it. And you can use that tag to find out whether the aspirin you are getting is original or not, whether it is expired or not. So you can use that, you can get this information by just scanning the tag. Another example of the item level cold supply chain and dynamic pricing. For example, you have this piece of meat in the factory, you put the label in it, then you transport it, and you can track it all the way. Then it's in the warehouse, maybe after the warehouse, it's in the retailer store. At the retailer store, for example, a person wants to buy that piece of the meat. So what he do, that he will scan the smart tag by using its mobile phone. When it scans the tag, it will get the information about the product. And the information of the person who is scanning the tag is also sent to the manufacturer plus the retailer, and that information can be then used for further providing the additional services to that person. I mean, that information can be used by other service providers to provide him or her other services. Now, what is the meaning of dynamic pricing here? Dynamic pricing means, for example, now there is a lifetime for a package of meat. Let's say the meat will be expired after 10 days. So let's say this is the 8th day of the meat in the retail store. So it's only 2 days left. After that, the meat is not useful for the retailer, not useful for the customer. So what retailer wants to do? He wants to sell that meat as fast as he can. So if he can do that, let's say by decreasing the price of the meat, because it is going to expire in next 2 days. So it will decrease the price. So nowadays, what he will do if he is using the tags, he has to put new tags with new prices in each of the package that is going to be expired. Okay, but in the case of smart tags, what happened that it can do it online. When the person or a customer that wants to purchase that scans the tag, it will get a different price. So this is the dynamic pricing based on the condition of the product. Then we have smart tags. How to create the smart tags? As I said, that we can use the functional links and NFC printed circuits to make a smart tag. And scanning. For the scanning, we need to build a standalone app that will scan the smart tags. We are not building any hardware. We will just build the app that will use to scan the smart tags. So if you want to scan the smart tag, then you just have to install that app from the App Store. So this is the stack. So this is the app, the scanning app that we are talking about, in which we will have 3 enablers. One that will enable the scanning process, second that will enable the authentication and IDM process, and third that will enable the context management enabler. So we are providing this layer we already have these layers and the upper application layer. So the project will work towards this layer, and it will provide the standalone SDKs for this layer that can be used on any platform. So these are the detailed functionality of these three enablers that the project will develop for the scanning process. Then we have few interesting use cases where this product can be used, and these are the use cases that the project is using during the course of its development. So first is the life cycle management. And this, for example, we have this product and the tag on it. If this product is exposed with the heat, then you can see that the circle disappears. So now this is unusable. Before that, it was usable. So these are the demos that are already there in the project, and we have shown these demos in the first review meeting of the project. Okay, so second is the smart bins, that you will take the vaccine, any vaccine, okay? You put the tag, you use the scanner to scan the tag. If the tag is okay, then you will direct it to the website where you can find all the details about the vaccine along with its authenticity and its validity, whether it's expired or not. But if this vaccine is going through some environmental changes, then after that you scan the tag and you will see, or you will get the information that the vaccine is expired, or it is invalid, or it is not usable. Then we have the recycling demo, in which when you use the item, after that, where you should recycle it. You go, there are 3 bins or maybe 4 bins, and at each bin we have the NFC tag. So when you go with the item, the right bin will blink. Maybe your phone will tell you that at what color bin you have to put that item in. So this is about recycling. Also, you can get the online information about the correct bin on your mobile phone, and it, along with its position, that where is that bin in which you can recycle this particular product. And of course, in this case, you can also put incentives to the users who recycles more. So in this way, the user will be benefited, as well as the manufacturing, or sorry, the companies that are handling the recycling process, they will also get benefited. Then we have one more use case about the brand protection, in which you can authenticate a particular product, whether it's genuine or not, with the help of smart tags. Okay, finally we have the challenges that one needs to address in order to get this project working. The first one is smart tags, how to create the smart tags, how to create them on a large scale to keep the cost of the smart tags low as much as it can, because we are saying that the smart tags will use the sensor data, they will transmit the data in the smart tags will change. So of course, we have to make the smart tags that are cheaper, that are of course smaller in the size, and that are also robust. So how to make such smart tags? So this is the first challenge. Second is the interoperability, that is how it can fit with the existing IoT infrastructure, or with the existing, if we are talking about the scanning process, we are talking about the tags, then how the existing standards can be used while making the smart tags and while using the smart tags. So the second issue is the interoperability. Then of course we have the security and privacy issues, because we need to scan data from the tags. So there is communication security while we are scanning, plus the application will run on a device, that is a mobile phone or maybe a scanner, a dedicated scanner. So we have to look about the hardware security along with the operating system security on which the application is running. Then the privacy issue, because the scanner are operated by the users. and the user has to send that information to the cloud. So along with the scanning information, the user information is also go to the cloud, and it is used by various service providers. So it should be done in a privacy-preserving manner. Then, in terms of technical uptake, that means how the output of the project will still be used after the end of the project. That means we have to build something that will work on the existing platform as well as on the cross platforms. Then data sharing. Then this is again related to the privacy, that how we can share data private by keeping the privacy of the user. So these are the details of these challenges. If we are creating a smart tag, then it should, we need to take care of the size, we need to take care of the technology, that it will work with the existing scanners, it will work with the existing inks, it can be printed with the existing printers, and so on. Okay, so for scanning, we need to take care about the reliability of the scanning. For example, if you are scanning by a certain angle, or maybe by a certain scanner, or by a certain distance, then it should be readable. Then what are the decoding schemes we put to decode the data in the scanners, and the authentication of the scanner with the tag should be on the fly, and it should be lightweighted. And of course, there are billions of the devices and the millions of the scanners, because we are talking about the crowdsourcing. So there will be millions of devices at the same time sending data to the cloud. So there are issues about the network latency and bandwidth, because the number of tags are too much, because we are talking about the product level tagging. So there are billions of the products. And of course, as I already told you, that we should make it usable across the IoT, across the existing IoT platforms. And it should work with all the different platforms. Like if someone is using cloud services from the Amazon, then it should be able to process the same data that are coming from the scanners, and that is scanned by the smart tags. And if someone is using some other cloud like Google, Microsoft, they all should be able to process that data and able to get services from, able to create services from that data. Again, it is a matter of interoperability, that all the standards that we follow to build this whole smart tag and smart scanners should be backward compatible with the existing standards of the communication, of the data sharing, and all those. Then this is another challenge, which is related to the data and device heterogeneity. So I have already talked about it. And then security at the device level. So as I said, that we have to ensure that the app is secure from the from the other apps that are running alongside with it, and from the operating system on which it is running. Thank you. For more information, you can log into the project website. Any questions?
Yes.
Okay. If there is more question, maybe I just lost it. How much data can a tag hold?
A tag hold. It
Yeah.
depends on the encoding scheme and the size of the tag, of course.
Okay. And the second is more of a remark. Since, for example, you just said that we need to go over this market entrance difficulty, but as of now, with Android, for example, we still don't have any system application to scan QR codes. And it's never going to happen, probably. We still need to use third-party things. So, given this, is there any hope for
You are
this
talking about the scanning
QR
app?
code? Yeah. Is there any hope for these codes? I mean, practical hope?
No, you are talking about the tags, or you are talking about the scanning app?
Yeah, the scanning stuff.
The scanning app.
Yeah.
So yeah, that's what we are
Those
saying.
codes are still-
Our aim is to build a scanning app that can run on the mobile phones, and with that scanning app, you can scan all this smart tags that will be built using the technology that is going that we will develop in the course of the product. Of course, still you can I think you can use the phone to scan the NFC tags. At present, you can also use the phones to scan the NFC tags. So it is already there.
Does the smart tag guarantee the originality of the source? Can we?
Originality of the manufacturer?
Yes, of the manufacturer.
Yeah, because the manufacturer is the one who is putting the tags at the first place.
Yes, no, I'm worried that I don't know. I'm producing a fake shoes of I don't know.
Yeah, but you are
producer.
but you are producing it by the name of your company.
No. I'm producing fake Nikes, for example.
Okay.
And I attack a smart tag,
Yeah,
but a fake smart tag that, okay, it has not the components that guarantees the correct delivery of the products.
Yeah, then at the time
you
of
can always have physical tags, like you can always take a tag from original packaging.
Yes, okay, the fact that
Yeah,
the first
of course,
idea was
we-
okay, I can.
we have to take care
Apply
that
a
the tags are not
physical
being copied. The first thing we have to take care that the tags are not being copied, and even if they are copied, then at the time when you are scanning the tag, it will contact to the manufacturer. Online, it will contact to the manufacturer and give you the answer about the authenticity. So
Yeah,
some
which
two
might
things.
be double check whether
Yeah.
those pair of knives should really be in the shop now.
Yeah.
Yeah.
Or whether they build
Actually,
a knife with
yeah.
that serial number or something like that.
So I have a question. So assume you're in the shop, and then I have, okay, basically my question was, at the very beginning, so you have like the tag represents like a chain or like a whole process of production or something. That's just a neat example. So I assume that each company that actually work on the meat, so from the producer to each steps, they add information to the tag. So it's a bit related to the size of the amount of information that can store into the tag. But my question is, so I assume that we have not enough space to have signatures, because I know that signatures are long. Like every producer puts his own signature on the data, puts on the tag. So I assume that this is not feasible to put all this amount of information into the tag. And my second question is, should I, in that case, have persistent connectivity, like keep having like, I don't know, HTTPS requests to one producer, to the other producer, to the other producer. So I have the information about the whole steps, and to be able to authenticate the all steps, I should actually be able to online contact each of the server of the producers. Is that correct? So this is actually the way I see this may work. And I want to know if this is the way the project
No,
envisions this
it is
work.
like that. If you, for example, a manufacturer has built a product.
Uh-huh.
At that time, he put a tag on it.
Mm.
Now the product goes from the manufacturing shop to the retailing shop, and on the way, no one is scanning it. On the way, no one is scanning it. So the manufacturer has that information. At this time, manufacturer has that information which he put on the tag, along with the information that he stored in his database about that tag and about that product. Okay.
In order to be able to, for me, to authenticate this information, should I
Yeah.
contact the server?
No, you won't contact to the server. When you scan the tag, then you are connected to the internet.
Okay, that was my question. So I must be online.
Yeah, of
I
course.
actually have
Yes,
internet.
yes, yes.
And so is that every tag has a manufacturer, or is like the tag contains information from different manufacturers? So so for example, I produce the meat, I put the tag, I produce the meat. So I give this to the transportation service, and they put another tag. So we have like a list of tags.
There is only one tag that is put by the manufacturer.
I see. Okay. So I see this is a bit inflexible, right? So it's like you have just the information on one manufacturer. So if I really want to add into, I would like to have information on the whole process, right? But anyway, so you have a tag, and then you actually need the other companies to add information to some centralized database.
At the center, not in the tag. At the center,
Yeah, I see. Okay. No.
Okay.
Okay.
Thank you.
Am I right here? Do you see me? That's right. No? Yeah. All right. So hi everybody, I am Alberto, and today I'm going to talk to you about bio things and bio networks. Oh, sorry, I forgot this. This is the witty quote by Richard Feynman that this is remarkably because in 1967, I guess, something like that, he first in the world started to talk about bio-nanothings, or at least nanothings in their beginning, and which are not simple downscaling things, but building, as a matter of fact, things from scratch, from something that already exists on nanoscale. So it is not like downscaling CPUs, things that we already do at the present moment. And the lecture that he gave was called "There's Plenty of Room at the Bottom," and this is why there's plenty of weakness at the bottom. So we are going to talk about, I need to introduce you a little bit of nanomachines and nano networks, and then the molecular communication, which is the way that nanothings communicate and build nano networks, the cooperation model that we use in our publication, and the security issues that we found which are related to this cooperation model, the attacks that we proposed and the related countermeasure. We will show a couple of graphs about the results that we got, and then we have the classical conclusion. So, what is a nanomachine? A nanomachine is a device in nanoscale, as we said, which is very simple and restricted. So you cannot think about a nanomachine like a full computer, personal computer that can do everything that a normal computer does. So you have simple ways of communicating. You can compute a little bit of data, and you can store a little bit of data. And these devices can be artificial or naturally occurring. It's the same. And clearly, the interconnection of these bio-nano things that makes a bio-nano network or a general nano network. And clearly, the communication is mandatory. So here we have an example of what a nanomachine, artificial nanomachine would look like, and right there we have a biological one. As you can see here, you can expect to have both in the artificial and biological, as an example, some sensors to gather information from the environment. So you have here 4 the sensors into the artificial one, and in the biological one, that is bacterium. By the way, you see you have the receptors just right there that gather information from the environment. You could have actuators, which are the parts that let the nanomachine to move around, and into a bacterium you have a flagellum or more flagella. If you think about a virus, and I'm not talking about viruses in a computer science way, but in a biological way, viruses, as an example, they do not have any kind of actuators because they get transported around, so they will not expose that characteristic. So how can we build these nanomachines? There is the top-down approach that, as I said before, is something like we have, at the present moment, we have some problems to keep on nanoscaling objects and things. So this is, at the present moment, not really achievable to further downscaling things. We could have the bottom-up approach, and which is combining individual molecules or even atoms, and thinking about them as Lego building blocks to build something bigger. Sadly, this technology does not exist yet. So the most promising one, which is the one that we are talking about today, is the biohybrid approach, which is taking already existing biological nanomachines like a bacterium and using that as a model or a building block to develop new nanomachines. So how these nanomachines can communicate? And the problem is that the standard solutions that we know for computer science are quite impractical, while solutions impede the mobility, and this is one thing that we really want into a nano network, because usually these nano things need to do something. They need to go around, search for something, move in a certain way, and so on. So impeding mobility is really undesirable. The wireless solutions, as we know, are hard to achieve because imply nano antennas, so you have to downscale antennas. And the biggest problem is that powering these nano antennas is really hard to do because they need a huge power harvesting mechanism. So this is hard to do. The solution is the molecular communication. What is it? The point is that molecular communication is the encoding of the information into molecules. And the nice thing is that the molecular transceivers are already existing in nature because bacteria have the capability to talk to each other and organize, and they use some chemo components. And another nice characteristic that we will see later in bacteria is called chemotaxis, which is the movement induced by chemical stimuli. So, as an example, bacteria can swim towards particles or away from poisons. What are poisons for the bacteria, like the salts? And bacteria, as I said before, can communicate through simple emissions, and they are able to even increase colony survival rates, do something really particular. They have nice characteristics. So we used in our publication a work by OK et al., published in 2014, which uses the cooperation of the chemo emissions to look in, as a matter of fact, for a previously known target. And this nano network of legitimate bionano things start from a single point. They start spreading around the environment, and as soon as one of these legitimate bionano thing finds the target, it will start to emit chemoattractants in order to attract all the other nano things and try to surround the target. As you can see here, and all the graphs that you are going to see are the average results of 20 panel simulations. You can see here that this target localization on the average at the end of the simulation, which is for 2000 seconds, you will have a 50% of legitimate binary things all piled up on a single point, which is the target location. So it functions quite well. So why do we need this? Why is this interesting? Because we could develop novel healthcare medical technologies. In 2016, this year, Okonkwo published a nice paper about targeted drug delivery, which is think about a cancer. At the present moment, you know, we have radiotherapy, chemotherapy, and so on, which is really hard on the human body, and we could think about these nano networks to be used to deliver the drugs specifically to the point where the cancer is. So you will have not all the hard things that you need to go through when you are under chemotherapy and so on, and that would be really good. We could have novel environment technologies like, you know, oil spilling containment. There are some bacteria there that are able to eat oil, and we could think about a nano network, nano bio things that is spread around on a oil spilling, and to help to contain it and make it disappear. We could think about water resources monitoring. So, you know, we would like to have the city wells safe and secure for the people. We do not like to for an attacker to spread, I don't know, anthrax or something like that. So we could think about a nano network which is floating on the water well, and as soon as someone, a bioterrorist or something like that, someone like him, tries to poison the water, we could have this live monitoring. So, as I said, counter bioterrorism, and that's for sure. Given that these are highly critical applications, the implementations should be really reliable, because we could make we could have a really hard problems and dangers to go through if the security investigations are not done properly. So, as I said, given that the implementations need to be really reliable, sorry, alliteration, the traditional security approaches are not suitable for the molecular communication, because we have not data encoded into bits, bytes, and so on. We have it is based on the presence, the absence, the different concentration of molecules. This is our information, and and even the physical architecture is completely different from a standard personal computer. So we have new kind of attacks possible, and therefore even the countermeasures needed are different. The point here is, and I want to stress it, that this is an unheeded problem, because before our work only 2 general surveys have been conducted in 2012 and 2014. So this is nanotechnology is getting more and more used around. It is somehow a buzzword, but the security investigations are at the present moment are non-existent. A huge problem. So we proposed 2 kinds of attacks, where some malicious binary things are spread into the environment, and their aim is to try to disrupt the communications between the legitimate binary things that are trying to get around the target. So the two attacks that we propose, namely the black hole attack and the sentry attack, are struck at the physical layer in the sub-layer, the signaling sublayer of the physical layer. So here we have an example. This is a black hole attack where you want to these malicious binomial things to stay far away from the target cells and start spreading attractants in order to drag near the legitimate binomial things. On the contrary, in the sentry attack, we want these malicious binomial things to stay around the target cells and spread chemorepellents to keep at bay the legitimate binomial things. So we proposed a countermeasure. You have to keep in mind, as we said before, that binomial things have really limited computing capabilities, so they are not able to do complex tasks. We assume that we know nothing about the environment, so how large, small it is, and we do not assume that we know the approximate location of the target, so the target is randomly positioned into the environment and we start from a random point. And even we do not assume that we know if there are these malicious binomial things and what kind of attack will be struck. We are trying to program this countermeasure into the legitimate binomial things without knowing what kind of these two attacks will be struck, if they are struck. And what we assume is that they are able to detect the real target once they are within range, and this is doable, understandable. I mean, as I said before, if we want to develop a binomial network that tries to detect anthrax spores, we know how anthrax spores are, so we are able to do this. What we want to do is, this is a little bit technical, but we want to change the HA threshold, which is a threshold under which the chemoattractants are not taken into account. And we want, and this is quite easy to do, compare the concentration of the chemoattractants and chemorepellents. So the point is that when the target is not found, the legitimate binomial things start from a single point and start spreading chemorepellents in order to spread more quickly. And this is their normal behavior. And so we will see that these legitimate binomial things will tend to spread around the environment. Once the legitimate binomial things find the target, at least one of them find the target, it starts to emit chemoattractants in order to call in all the other spread legitimate binomial things. So the point is that once the target is found, if we have a concentration of legitimate binomial things around the point, it does mean that we have found the target, and we expect from them, from all of them, to emit chemoattractants. And this is the crucial point of our countermeasure, because if we are a legitimate binomial thing and we are stacked up on a single point with all the others, and I do not sense any kind of chemoattractants, it does mean that I am with all the others on a single point without any kind of reason, because I should detect the target, I should be emitting chemoattractants, and all the others should do that. So this is the trigger of a possible ongoing attack. So as I said before, this is why we want to check the ratio of concentrations, because if I sense a huge concentration of chemorepellents compared to the chemoattractants, maybe I am getting trapped by the attacker, so I want to get away, and I want to stop sensing for some kind of time, so a limited time. I want to stop sensing the chemoattractants in order to tend to spread again. And this is our aim, as I said. And the point here is that how do we compute this concentration of this ratio of concentrations? We even proposed two different kinds of decision processes, which is the threshold-based approach and the base rule. The threshold base is quite simple. This is this equation which is fixed, and you will have here the initial concentration of the attractants and so on. This n of LBNTs is the number of legitimate binary things. So this, which are present into the neural network. So this equation is flexible with the number of legitimate binary things that we introduce into the environment. And the point here, as I said before, that if the chemoattractants, which are on the left side, are less than the chemorepellents, then they are ignored for some time. And it is simple and effective. We will see this later, but it lacks the flexibility because it is fixed, as we said. So the other approach is the Bayes rule, which is this posterior knowledge got by improving the prior knowledge, which is P as E, and so on. And this formula is and we will see later how we implemented that. This is more flexible than the threshold-based one. The point is that creating this approach is quite tricky because you have many parameters to set. So we focused on 4 different functions because usually a Bayes rule results in a sigmoid function. So we said, all right, we will try to our Bayes approach with 4 different sigmoids, and we will choose the ones that behaves better than the others. And as you can see right there, this is the sigmoid function that we used in all our testings later. So here we have the results. The point is that the black hole attack is extremely disruptive, and here we have a black hole attack struck without any kind of countermeasure, and the red ones are the legitimate binary things that are attracted towards the malicious barycenter, and the red line is the legitimate binary things that get the real, the intended target. As you can see here with the black hole attack at the 1000 seconds, all the legitimate binary things are attracted into the trap, and they stay there. They are not able to get away without countermeasures. With the threshold approach, the results are really better. You can see we have quite none legitimate binary things that get near the barycenter, and they, on the average, only 30% of legitimate binary things that get near the target. And the Bayes approach is the best one, as we said before. Non-legitimate binary things that get near the barycenter, and quite a 50-60% of legitimate binary things that get to the intended target. So what we get from our data, well, we get the more the black holes that we inject into the environment, the harder it is to get away. This is clear. So as you can see here as an example, you see here that it is easier to get more legitimate binary things near the target with only 1 black hole injected. And when we have 4 black holes injected, the results are not so good. And what we get, even by this, we get that the higher the number of the legitimate binary things, the better, more or less, are the results. As you can see here, given that this is completely random, this is a tendency, not something regular for all our results, but it is clear that on the average 200 legitimate binary things, you can see here the orange one, get better results than 50 legitimate binary things into the environment. So this is an example of how they will behave. As you can see here, they start from this center point and they start to spread. And if we have no countermeasures, they will all tend to get here into the barycenter of the 2 malicious binary things. given that we implemented the countermeasure, you can see there that someone here has found the target and starts spreading the chemoattractants. So all the other legitimate binding things will tend to get there, and in the end, it is for 1,600 seconds. You have all the legitimate binding things around the target and not around the center of black holes. The central attack. So the central attack is by design really less disruptive than the black hole one, because as I said, by design, the legitimate binding things as we implemented them, and as OK et al. Implemented them, are more sensible to the chemoattractants than the chemorepellents. So, given that, they will be more sensible to chemoattractants attacks than to chemorepellents one. So, what we wanted to be sure is that our countermeasure, our general countermeasure, do not worsen the situation, doesn't worsen the situation. So here, this is the graph that we have seen before. This is the 100 legitimate binding things without attacks. And right there, you see that what we have with an attack without countermeasure, with the threshold and the base countermeasure. And as you can see, the results are more or less the same, even a little better with the threshold and base approach than the no countermeasure. So we are able to say that you have the 30% on the average of the end, at the end around the legitimate binding thing. So we are able to see a strange concentration of legitimate binding things around a single point. So we are able to detect an attack, and our countermeasure does not worsen this result. So we are, it is safe to implement this countermeasure, even if a central attack is struck. So conclusion, the attacks are feasible. As we said, the black hole is highly disruptive, and the central attack not so much. The countermeasure that we implemented is simple enough to be implemented into a binary thing, and it is even pretty effective to mitigate the danger. And the Bayesian approach is more consistent than the partial one. So this is all the references and so on. This work has been published on transactions on information forensics and security in 2016 paper. So I'm finished. If you have any questions, you're free to ask. Yes.
So I have a question about the very last couple of slides. So basically, if I understood correctly, so this graph exactly, what you're trying to assess is that if with the other countermeasure for the black hole, you're not worsening this other attack, right?
Yeah, that's it.
And,
because you have the point is that if we develop two different countermeasures, we should be able to know on a prior basis what kind of attack will be struck. So given that the central attack is not so disruptive, we are able to have just one countermeasure that functions for the black hole attack, which is the disruptive one, and we are still able to detect the target even if a central attack is struck. This is
how do you do these evaluations? It's like a simulator?
Yeah, this is a simulator that we wrote, and the problem here is that wet lab experiments are highly costly, and so before going through a biology lab and so on,
so you know how this it's like I don't remember exactly how that substances expand, right? Like simulations.
Yeah. So as all the simulations, you have some assumptions, some things that.
You have to discretize them.
Yeah, you have to. But this is just to make an initial assessment of the things, and it is promising as it seems. You go through wet labs, and you check in reality how it works.
And another question is, what's the other future work on this? Do you have any plans?
Yeah, we are working at the present moment with Professor Conti about a positioning system for these bioimmuno things based on the gradient of the concentration of these chemo components. So we are writing a couple of papers. You see, this is quite a, as I said before, it is an unheated problem at all. So we have ample spaces to publish and to research, because there is quite none that is publishing about this.
Okay.
Questions? If not, let's this was last talk, so this also conclude the workshop. So let me just thanks again, close it, and association for Continuous Unity, which is co-organizing this workshop. Thank you.